So that was d loss by d log prob. Next is d loss by d probs. This is the function I does. It takes the log of all of the it's pretty simple. That's one my answer. Actually, the probs will again have the same size as that of log probs. And each of the variable in there, right, will be 1 by x. Whatever the value it is, right, that will go down as 1 by x of this. That needs to be multiplied by these gradients as well because of the chain rule, right? So it's like uh, probs lead to probs, and then we get the loss. So if we need to get the loss by the probs, that will be equal to d log probs by, that is the chain rule, that's what I'm applying. Loss. Sorry, this is ulta. No, this is fine. Obs by D probs. This is what we calculated, right? Wait. So dz by dx, dz by dy, impact of x on y and y on z. Okay. So impact of prob, impact of probs change into deprobs. This should be. So that is with respect to d log probs, how logs is changing, and based on d probs, how d log probs means if we change this, how this is changing, that is all. If we are changing this, how this is changing, and then if we are changing this, how this is changing. So if we are changing this, how this is changing. So that will be d logs by d log probs, okay? So to calculate this, right? So this is what we need to calculate, and this is simple, right? We are just taking the differentiation of the values there. So if you see, right, we're doing the probability what we are doing a log, right? So whatever is there in log probs, prob is one thing, on that we are applying log, we are getting log probs. Not this one is whatever. Yeah. So this means what differentiation of sorry, log x equal to 1 by x. Okay, so in the same way, there what we are calculating log probs and we are getting log probs. So differentiation of this will be equal to 1 by probs. Okay, so sorry, probs we are doing a log and getting a log prob, right? So it will be simple probability. So the size remains the same, and for each individual variable we need to do 1 by x. Or underscore n This is a step, so we need to go through each of the individual variable and need to do a 1 by x. I don't know if there is a easier method to do that, but anyway, we'll learn from Parvati. Um, feel pretty strong. There is a good way of doing the same thing that I will doing. Mm. This element-wise log itself for each of them.
Probs depends on probs through a log. So all the elements of probs are being element-wise applied log to. Now, if we want deep probs then remember your micrograph training. We have like a log node. It takes in probs and creates log probs. And deep probs will be the local derivative of that individual operation, log, times the derivative.
Oh, I missed the time spot. Getting it right. So this is what the chain rule I told, right? Good. And this should be the d loss by d log props. That's what we calculated in d log props I j. I think, yeah. No, it's true.
Derivative loss with respect to its output, which in this case is d log probs. So what is the local derivative of this operation? Well, we are taking log element-wise. And we can come here and we can see, well, from alpha is your friend, that d by dx of log of x is just simply 1 over x. So therefore, in this case, x is probs. So we have d by dx is 1 over x, which is 1 over probs. And then this is the local derivative. And then times, we want to chain it. So this is chaining times d log probs.
It's that simple. Yeah, I should learn how to. Oh, it works.
And let me uncomment this and let me run this cell in place. And we see that the derivative of probs that we calculated here is exactly correct. And so notice here how this works. Probs is going to be inverted and then element wise multiplied here. So if your probs is very, very close to 1, that means your network is currently predicting the character correctly. Then this will become 1 over 1, and d log probs is just gets passed through. But if your probabilities are incorrectly assigned, so if the correct character here is getting a very low probability, then 1.0 dividing by it will boost this and then multiply by the log probs. So basically what this line is doing intuitively is it's taking the examples that have a very low probability currently assigned and it's boosting their gradient. You can
Okay.
look at it that way. Next up is
making right prediction, making right prediction. That is one. Next, what we are doing is with respect to this individual, I guess, count some inverse. So this is what count and then by sum of that. That's what is happening here. So if we do it here, right? So what is happening there is I'm taking each individual variable and doing it so it's something like if x was it, I'm doing it x by sum of, you can say, x plus, oh sorry, x, y, z. Just for an example I'm taking. And that's what is giving us the props. So as of now, we have calculated with respect to probes how the loss is changing. Now we need to calculate uh, how is loss impacted by d of x. And again, applying the chain rule, d of probes by d of x into d loss divided by d probes. This is what we calculated just now on the top, d probes. Okay, so this is something that we need to calculate. That will be equal to d of probes, that is equal to d of x by x plus y plus z. Okay, by d of x, and into it is, I will call it as d props. That's what we calculated here, right? Now mm, we can take it in two ways. Let me see. So d, I will make it as a multiplication rule and say it is x plus y plus c to the power minus 1. Okay, dx. We will assume so this I'm doing separately. Okay, here because this is multiplication. So what will happen is, sorry, x plus y plus c minus 1 into dx by dx plus x will come out into d of y dx. That's what happens, right? Multiplication. We take this as sort of a constant, it comes out and we differentiate by. So this is anyway 1. Um, so here, right, this will come out plus x. Sorry, I missed one. X into derivative of 1 by. Okay, so so the minus 1 will come out. Okay, so n came out, power reduced by 1 more, so this will become minus 2 into differentiation of the inside, so dx by dx will be 1 plus 0 plus 0, so it will be 1 plus 0 plus 0. Okay, the differentiation of this. If we have to simplify, this will be this. Okay, 1 by x plus 1 by x minus, if I take the minus 1 right now, x divided by the sum square. That's what it is. So you can say 1 by sum minus x by sum square. Okay, so 1 minus by sum square, 1 by sum, if I take outright 1 minus x by sum. So for we have the sum, right? Um, so counts are all the x. So it is something like this. Okay. So in this variable, right, x was the count and ax plus y plus b was the so where it is, yeah, this individual. Okay, minus 1. This is the sum inverse. Okay, so if I have to calculate all of the gradients, okay, so I take this as common, right? It will be 1 minus x by this guy. Okay, that will be equal to. So here I can write count inverse into 1 minus x is the count this is the gradient. So this is d d count sum inverse. Hopefully this should give us something. Let's see. We count is not defined as count section. Okay. Tensor. Okay. Sorry, it's multiplication. So one I again missed the chain rule. So this gets, so I forgot this part. So I calculated this one. I forgot this part. Okay. Now, so now, so that this gets calculated. Okay.
Count sum inf. So we want, that's a little bit confusing. We have the logits that come out of the neural net. Here what I'm doing is I'm finding the maximum in each row, and I'm subtracting it for the purpose of numerical stability. And we talked about how if you do not do this, you run into numerical issues if some of the logits take on too large values. And we talked about how if you do not do this, you run into numerical issues if some of the logits take on too large values, because we end up exponentiating them. So this is done just for safety, numerically. Then here's the exponentiation of all the sort of like logits to create our counts. And then we want to take the sum of these counts and normalize so that all the probs sum to 1. Now here, instead of using 1 over count sum, I use raised to the power. That there's something wrong with the PyTorch implementation of the backward pass of division. And it gives like a weird result, but that doesn't happen for star star -1. So I'm using this formula instead. But basically, all that's happening here is we got the logits, we want to exponentiate all of them, and we want to normalize the counts to create our probabilities. It's just that it's happening across multiple lines. So now, here, we want to first take the derivative, we want to backpropagate into count sum inf, and then into counts as well. So what should be the count sum inf? Now, we actually have to be careful here because we have to scrutinize and be careful with the shapes. So counts.shape and then count sum inf.shape are different. So in particular, counts is 32 by 27, but this count sum inf is 32 by 1. And so in this multiplication here, we also have an implicit broadcasting that PyTorch will do, because it needs to take this column tensor of 32 numbers and replicate it horizontally 27 times to align these two tensors so it can do an element-wise multiply. So really what this looks like is the following, using a toy example again. What we really have here is just props is counts times count summand, so it's C equals A times B, but A is 3 by 3 and B is just 3 by 1, a column tensor. And so PyTorch internally replicated this elements of B, and it did that across all the columns. So for example, B1, which is the first element of B, would be replicated here across all the columns in this multiplication. And now we're trying to backpropagate through this operation to count sum in. So when we're calculating this derivative, it's important to realize that these two, this looks like a single operation, but actually is two operations applied sequentially. The first operation that PyTorch did is it took this column tensor and replicated it across all the columns, basically 27 times. So that's the first operation, is a replication. And then the second operation is the multiplication. So let's first backprop through the multiplication. If these two arrays are of the same size and we just have A and B, or both of them 3 by 3, then how do we backpropagate through a multiplication? So if we just have scalars and not tensors, then if you have C equals A times B, then what is the derivative of C with respect to B? Well, it's just A. And so that's the local derivative. So here in our case, undoing the multiplication and backpropagating through just the multiplication itself, which is element-wise, is going to be the local derivative, which in this case is simply counts, because counts is the A. So this is the local derivative, and then times, because of the chain rule, d props. So this here is the derivative, or the gradient, of with respect to replicated. But we don't have a replicated B, we just have a single B column. So how do we now backpropagate through the replication? And intuitively, this B1 is the same variable and is just reused multiple times. And so you can look at it as being equivalent to a case we've encountered in micrograd. And so here, I'm just pulling out a random graph we used in micrograd. We had an example where a single node has its output feeding into two branches of basically the graph until the loss function. And we're talking about how the correct thing to do in the backward pass is we need to sum all the gradients that arrive at any one node. So across these different branches, the gradients would sum. So if a node is used multiple times, the gradients for all of its uses sum during backpropagation. So here, B1 is used multiple times in all these columns, and therefore the right thing to do here is to sum horizontally across all the rows. So we want to sum in dimension 1, but we want to retain this dimension so that the count sum in and its gradient are going to be exactly the same shape. So we want to make sure that we keep them as true so we don't lose this dimension. And this will make the count sum in be exactly shaped 32 by 1. So revealing this comparison as well and running this, we see that we get an exact match. So this derivative is exactly correct.
if we calculate this right, some will be equal to 1. If we change x because it's sometimes by the same actually is reference to will be 1. And